Ionic equilibrium. In this lecture, I will be talking about these topics I have mentioned here. Arrhenius concept of acids and bases, then Bronsted-Lowry concept about acids and bases, Lewis concept about acids and bases. After that, some introduction about ionization of acids and bases. In detail, I will be talking about in the next lecture. And then ionization constant of water and its ionic product. The first one, we need to understand when we say strong acid, strong base, weak acid, weak base, or electrolytes. All these are electrolytes, means they are dissociated in water completely. We say strong electrolytes, whether it is base, acid, or salt. So for example, this is salt, NaCl gets dissociated almost 100%. Then CaCl2, again another salt, gets dissociated 100% in water. NaOH, this is base, caustic soda, sodium hydroxide, gets dissociated almost 100%. So we will say these are strong electrolytes. Weak electrolytes will give us equilibrium. So most of the time we will be interested in equilibrium here. So it means we will be dealing with weak acids, weak bases, weak salts, like that. Okay. Suppose acetic acid, this is weak acid. Ammonium hydroxide, this is weak base. Means they will have appreciable amount of all, that is reactants and bases. Here, products. Next, Arrhenius concept of acid and bases. Simply, if any compound gives hydronium ion is hydrogen ion combined with water. So proton does not exist as H+. There is no existence of H+. H+ actually combines with water molecule, means it gets hydrated and then gives you hydronium ion. Hydronium ion. So in this chapter, whenever I say hydrogen ion, actually we will be talking about hydronium ion, because H+ does not exist. So this concept is, if it is acid, it will give you H+. For example, HCl. HCl gives you H+. It means this is acid. Okay. H2SO4 gives you H+, and HSO4 minus means you get proton. It means it is acid, as per Arrhenius concept. Bases will give you OH minus. So if I talk about base will give you OH minus. NaOH, sodium hydroxide, this is a base. It gets converted into Na plus and OH minus. It means it is a base. Ammonium hydroxide, it gives you ammonium ion and hydroxyl ion. It is a base. The difference is NaOH is a strong base. It will get dissociated into sodium ion and hydroxyl ion almost 100%. NH4OH is weak base. So there will be some equilibrium here. So that's why equilibrium sign will be here. In general, we can say HX will give you H+. And if it is a base, it will be MOH, where M is any metal. Group 1, group 2 elements normally will be there. Then Bronsted-Lowry acid and bases. Bronsted-Lowry acid and bases, acid concept is same as Arrhenius. Means if it gives a proton, it is acid. But Bronsted-Lowry concept does not deal with hydroxyl ion, only H+. If it donates proton, it is acid. If it accepts proton, it's a base. That's it. Then there's a concept of conjugate acid and base, because here we don't deal with hydroxyl ion, it is only the H+ ion. So if I say there is HX, okay, and it gives you H+ and X-. So as per both Arrhenius concept and Bronsted-Lowry concept, this is acid. But as per Bronsted-Lowry concept, because after losing hydrogen, you get X-. So this X- is called conjugate base of HX. Now there is reason why. We know HX is acid because it has donated proton. Why this X minus is conjugate base? Because as per definition from Bronsted-Lowry, base is that one which accepts proton. So if you do the reverse reaction here, in that case, it is clear that X minus is accepting a proton and then getting converted to HX. It means this is a base which is getting converted to an acid if it accepts the proton. So in this case, because we got a base from acid, we call conjugate base of that acid. Similarly, if we consider X minus as base, HX will be conjugate acid of X minus. So conjugate acid, conjugate base concept is limited to Bronsted-Lowry only, not to Arrhenius and not to Lewis concept, which I will be talking about later. Conjugate pair of acid base differ only by one proton. So this is something you have seen here. I have given you example. HX gives you H plus and X minus. So these two differ just by a proton. So this is a very quick way to find out that this is a pair of conjugate acid and base. There should be difference of one H plus ion only. This is an example. Ammonia when dissolved in water, remember ammonia is water soluble, okay, so you can dissolve it in water, gives you ammonium hydroxide. This is ammonium hydroxide and H4OH, which is in ionic form because it is in water. There is some equilibrium here. If it is equilibrium, both reactants and products will be present at equilibrium. It means water will be there. If water will be there, these two will get ionized, okay. It will not exist as NH4OH, rather it will exist as NH4 plus and OH minus. Now see here, if I consider NH3 to NH4 conversion, there is difference of 1 H plus. If you add proton here, you will get NH4 plus. So because this one is accepting proton to get converted to this one, it means this is what? This must be base. And in that case, this will be conjugate acid. Conjugate acid of what? Of ammonia. Now consider the other one. It loses proton, means donates proton. If it donates proton, it means it is acid. So this is acid and this will be conjugate base of what? Of this acid, that is H2O. Now a question, just to understand whether you got the concept or not. What will be the conjugate basis for the following Bronsted acids? So it is already given. Sometimes it will not be given. You will be asked that whether it is acting as acid or it is acting as base. You will find on the basis of whether it is losing proton or gaining proton. Here, these are acids. It means they will lose proton. So HF, when it loses proton, will give you F minus. After losing this proton, it will give you F minus. It means the conjugate base of this one is F minus. This is the conjugate base. So whatever you get after removing H plus, because it has donated, it has been removed, the remaining will be conjugate base. So here in this case, the conjugate base of HF will be F minus. Now come to this one, remove one H plus from here. So H2SO4, when it gets dissociated, it will give you H plus and remaining HSO4 minus, means whatever is there after removal of H plus, that will be conjugate base. HSO4 minus in this case will be conjugate base. Now come to here, HCO3 minus, remove one H plus. So if you have removed one H plus here, then you will have only CO3, but on both sides, left hand side, right hand side, the charges must be balanced. Here you have -1 charge overall, and here you have +1. To have overall -1, here you must have 2 minus. So here -2, now total is -1. So left hand side, right hand side charges must be equal. So what is conjugate base here? Carbonate ion, CO3 2 minus. Next, Write the conjugate acids for the following Bronsted bases. Even if Bronsted is not written, you should understand it is applicable only for Bronsted-Lowry concept. Okay, so these are bases. If these are bases, they will accept proton to get converted to acid. So when NH2 minus accepts proton, it will get converted to NH3. And what will be the charge? Here overall charge is -1 + 1, that is 0. So on right hand side it should be 0. So ammonia obviously does not have any charge. So it is NH3 in this case, ammonia. Okay. Second one, if we have ammonia, ammonia can act as Bronsted base. So ammonia can accept proton again. Now it will be NH4 and total charge here is +1. So +1 charge must be there. It means ammonium ion will be created. Next is HCOO minus. HCOO minus. Okay. When it accepts proton, it will give you HCOOH, formic acid. Formic acid. That is the answer. Next question. The species, given a species, can act both as Bronsted acid as well as bases. Now you need to give Bronsted base and Bronsted acid of each. It means H2O can donate proton, can accept proton. Depending on that, it will be treated as Bronsted base or Bronsted acid. So if it donates proton, it will be treated as acid. If it accepts proton, it will be treated as base. So for this case, H2O, if we talk about conjugate acid, it means it will give you conjugate acid when itself it acts as base. So if it acts as base, then it will give you conjugate acid. And when it is acting as base, it means it will accept proton. So if it accepts proton, it will give you hydronium ion, H3O plus. When H2O gives you conjugate base, it means at that time it will act as acid. And when it acts as acid, it means it will donate proton. So just remove one hydrogen with positive charge. So if you remove one hydrogen, it is just OH and minus charge will be there. Why? Because H2O, when it donates proton, means this proton is separate. Here OH has to be minus because here there is no overall charge. So here also charge sum should be 0. So after donating this proton, the left is conjugate base. HCO3 minus, it will act as base when it gives you acid. So when it acts as base means add H plus into it. When you add H plus, it will give you H2CO3. When you remove H plus, it will give you CO3 2 minus. Next one, HSO4 minus. It is similar to second one, HCO3 minus. You will get acid. It is acting as base. It accepts proton to get conjugate acid. It means it will be H2SO4. For this one, it will act as acid to give you base, and it can act as acid if it donates proton. So remove H plus. When you remove H plus from here, you will get SO4 2 minus. Next one, NH3. NH3, when it acts as base, it means it will accept proton. When it accepts proton, it will give you NH4 plus. When NH3 donates proton, it will give you NH2 minus. Remember, the charges have to be balanced. So basically, if you consider this one, this is plus H plus. It accepts because it is acting as base for this one. But if you are considering this one, it will donate H plus. So the sum of charges here again 0. Okay, here it was 0. Now Lewis concept of acids and bases. Till now we were talking about the acid and base in terms of H plus OH minus only, right? But Lewis concept is based on electrons, nothing about H plus or OH minus. If it can accept electron pair, then it is acid. If it can accept electron pair, it is acid. if it can donate electron pair, then it is base. You have to remember these concepts. However, it is easy to understand if you compare it with the Bronsted-Lowry concept. Okay, compare it with Bronsted-Lowry concept. Bronsted-Lowry concept is, if it is acid, it will donate proton. Proton means positive. And if it is base, base will accept proton, means positive charge. And what is Lewis concept? Lewis concept is in terms of negative charges, electrons, electron pair. So it means in this case it will be acid will accept electron because it is negative charge. So it is same thing. Either you donate positive, either you give positive, or you accept negative. Both are same thing. Base, as per Bronsted-Lowry, accept proton, that is accept positive. Here donate negative. So bases will donate electron, that is negative pair. It is pair we will be talking about, not one electron. And you might be surprised why I am talking about electron pair. The reason is very simple. The charge, positive or negative, will be only in heterolytic cleavage. So if I have A, B, and only one electron goes, then it will, the one will accept one electron, another one will accept one electron. None will get positive or negative charge. If you see one should have positive charge, then it should be heterolytic cleavage. In this case, it will be A plus and B minus. So only in that case, we will treat it as H plus, for example. Okay. So that's why we talk in terms of electron pair, not single electron. In Lewis concept, many acids do not have proton. So why this concept was brought in? The reason is, if we think first, Arrhenius concept. Arrhenius concept talked about H plus donation, OH minus donation. Okay, but there were many bases which did not have OH minus, but still they were acting as bases. So that's why Bronsted-Lowry concept came in, that if there is only H plus, it gives H plus, it is acid. If it accepts H plus, it is base. So there was no requirement of OH minus in that case. But still there were few compounds which acted as acid or base, and they didn't have hydrogen at all. Okay, they did not accept hydrogen, they did not have hydrogen to donate. For explanation of those type of compounds, Lewis concept was adopted. Okay, because every compound has electrons, so Lewis concept is applicable everywhere. To understand it, I will give you the example also where it will not have hydrogen, it will not accept hydrogen, but still it will act as acid. A typical example is reaction of electron deficient species BF3 and NH3. So in this case, what happens? BF3, if you see, BF3 is like this. Boron has atomic number 5, that is 2,3, electronic configuration 2,3, 3 valence electrons, and all 3 valence electrons are here occupied, and fluorine's electrons here. So the valence shell has how many electrons? 6 electrons only. It means it is electron deficient. Boron trifluoride is electron deficient. It means it tends to accept an electron pair to have complete octet. So it will accept electron pair, that is 2 electrons, there will be 8. And as per Lewis definition, if it accepts electron pair, then it is acid. So it means boron trifluoride will act as acid. Now NH3, if you see, nitrogen has configuration 2,5, 7 electrons total, 2,5, 5 electrons in its outermost shell, out of which 3 are connected to hydrogen, and the rest 2 electrons form electron pair. So this ammonia can donate this electron pair to BF3. Means there can be coordinate bond formed. So what actually happens that BF3 and there is NH3, these two electrons are on ammonia are shared to form a covalent bond, which in this case will be coordinate bond because both the electrons are from nitrogen. So there will be a bond between nitrogen and boron, which is a type of coordinate bond, but both the electrons are from nitrogen. So we will have arrow here just to show that this is coordinate bond. In this case, NH3 is donating electron pair, so it is base. BF3 is accepting electron pair, so this is acid. And there is no transfer of hydrogen, etc. Next question, classify the following species into Lewis acid and Lewis base. So you just need to apply the definition. If you are confused, first write the definition. Lewis acids are electron pair acceptors. Okay, bases obviously will be donors, so I'm not writing it. Now consider one by one. OH minus. OH minus has a negative charge. If it has negative charge, it means it can donate electron pair. It already has negative, it will not accept negative. So if it can donate electron pair, it means it will act as base, Lewis base, because it can donate an electron pair. Next one, F minus. F minus already has negative charge. Its octet is complete, right? Fluorine has 7 valence electrons, one more 8. So it will not donate, it will not accept the electron pair. Rather, because fluorine will have these electron pairs, it can donate these electron pairs. So fluoride ion will also act as Lewis base. Now the next one, H plus. H plus has positive charge. It cannot accept positive charge. Means it can accept electrons. It already has positive charge. It can accept electrons. It does not have any electrons to donate. H plus has 0 electrons. So it means it can only accept electron pair. It means it is acid, Lewis acid. Next one, BCl3. BCl3 is similar to BF3. It is electron deficient. So BCl3 is like this. There are 6 electrons in its valence shell. It is electron deficient. It will tend to accept electron pair to complete its octet. It means Lewis acid. Now ionization of acids and bases. Overview here in detail I will be talking about in next lecture. When we say strong acids, you have to remember few acids in your test, in your exam. It might not be written that these are strong acids or weak acids. You have to identify, and on that basis, obviously, you will do the calculations. So perchloric acid, HClO4 is strong acid, means it will get dissociated almost completely in H plus and ClO4 minus ions. Hydrochloric acid, hydrobromic acid, and hydroiodic acid. All these three, HCl, HBr, HI, are strong acids. They will get converted into their ions almost completely. Then nitric acid, H plus and NO3 minus, is strong acid. And sulfuric acid, H2SO4. You must remember these 6. If these appear in your exam, you have to consider them as strong acids. Then strong bases, you need to memorize lithium hydroxide LiOH, sodium hydroxide NaOH, potassium hydroxide KOH, cesium hydroxide CSOH, and barium hydroxide BaOH. Normally these one will be group 1 and group 2 hydroxides, okay, but not group 2 towards the top. For example, beryllium hydroxide will be covalent, okay, so not much ionic. Similarly, magnesium hydroxide also not much ionic. but these are very strong bases. The strength of an acid or base may be gauged in terms of Bronsted-Lowry concept of acid and bases. Okay, so in Bronsted-Lowry concept, we said that if it can donate proton, it is acid. If it can accept proton, it is base. Here what we can say, to measure the strength, we can say how easily it can donate proton, how easily it can accept proton. That will decide how strong the acid or base is. So you will need this knowledge to get the answers for arrange these in increasing order of their basic strength or in acidic strength, like that. So how easily it can donate or accept proton, you will decide on that basis is strength of the acid and bases. So a strong acid means a good proton donor, it can donate the proton very easily. A strong base, good proton acceptor, it can accept proton very easily. Consider the acid-base dissociation equilibrium of a weak acid HA. HA, for example, HCl. Okay, but here HCl cannot be there. The reason is HCl is strong acid. So if I say HA, it can be A, here can be CH3COO, because CH3COOH when gets dissociated will give you CH3COO, H plus and CH3COO. So it means this is H and this is A. We are considering weak acid. So in such cases, what will happen? Try to understand. Yeah. In such cases, here it is donating proton. Okay. So when it donates proton, you get this one. After removing proton from here, you get A minus. It means this is acid, its conjugate base will be when you remove proton. Here water is acting as base. Why? Because it is actually accepting the proton which was donated by acid. It is accepting the proton to get H3O plus. So H2O is base and hydronium ion in this case is conjugate acid. Now what is important to remember? The equilibrium moves in the direction of formation of weaker acid and weaker bases. And the reason is very simple. Because weaker acid and weaker base will not get ionized. We know, we have talked about, if I go back, strong acid and strong bases we talked about. It means they fully get converted to their ionic forms. If these are strong, these will get converted to their ions almost 100%. And when it is possible if backward reaction is not possible. Otherwise, there will be some equilibrium. So there is no equilibrium here, almost no equilibrium. The reason is very simple, because the reaction is only in one direction. The reason is very clear, because here it is very strong. And to ensure that reaction does not happen in backward direction, it means these are very weak electrolytes. Only then it is possible that reaction is in one direction only. So for strong acids, the conjugate base will be very weak and vice versa. That's what we are talking about here. The equilibrium moves in the direction of formation of weaker acids and weaker bases, because the stronger acid donates a proton to a stronger base. That is, strong acids have very weak conjugate base and strong bases have very weak conjugate acid, and vice versa. Strong acids like perchloric acid, we have talked about all these 6: perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid, will give conjugate base ions, these which will be weaker bases, which will be very weak bases. And the reason is very simple, because all these acids are very strong, they will give you very weak bases. So if this question is asked, simple concept applicable here. And as compared to what? As compared to water. Water is considered to be neutral, so that's why as compared to water. A very strong base would give a very weak conjugate acid, and vice versa. Same thing here. So for example, NH2 minus, O2 minus and H minus are very good proton acceptors and thus much stronger bases than water. So just you can remember, these are very strong bases. Now ionization concept of water and its ionic product. Basically ionization constant and ionic product of water, these are same thing. Okay, you will see. Water can be represented like H2O, one molecule reacting with another molecule of H2O and giving us hydronium ion and OH minus. Water can act as acid as well as base. So in reality, what we can see here, one molecule of water acts as acid, another molecule acts as base. Why? The reason is very simple. One molecule, it is acid, acting as acid, it will donate proton. And when it will donate proton, it will get OH minus. So if it is acid, OH minus will be its conjugate base. This molecule of water is acting as base. It means it will accept that proton and will get hydronium ion, and hydronium ion will be conjugate acid of this base. This is the equilibrium reaction of water. Now if I write the equilibrium constant for this one, equilibrium constant in this case is also known as dissociation constant because water is getting dissociated into hydronium ion and hydroxyl ion. This is hydronium ion, this is hydroxyl ion. But what you note here, on the left hand side, this is 2H2O, that's why I have here H2O whole square. This is pure liquid, and for pure liquids and solids, the concentrations are not considered in equilibrium constant. It means effectively you have dissociation constant as H plus and OH minus only, hydronium ion and hydroxyl ion concentrations only. This H2O will be treated as constant and will be merged with this one. And we will get the dissociation constant of water as hydrogen ion concentration multiplied with hydroxyl ion concentration. Remember, we can write it as hydronium ion concentration multiplied with OH ion concentration as well. It is same thing. Okay, so whatever number of H plus you will have, if it combines with H2O to give you hydronium ion, same number of hydronium ions you will get. So suppose you had 1000 hydrogen ions, they will combine with 1000 water molecules and will give you 1000 hydronium ions. So the concentration will still be same, the molarity will still be same, whether you consider it H plus or you consider as 3O plus. Same thing. This is something, whenever I write something in green color, means you need to remember this formula. You will be using this formula directly in numericals. So write it somewhere. The concentration of hydrogen ion has been found out experimentally as 10 to the power minus 7 m. That is the molarity of hydrogen ion in water has been calculated by experiments as 10 to the power minus 7 at room temperature. Room temperature is 25 degrees Celsius or 298 Kelvin. As dissociation of water produces equal amount of H plus and OH minus, you know H2O gives you 1 mole of H plus and 1 mole of OH minus. It means same will be the molarity of hydroxyl ions as well, 10 to the power minus 7 moles per liter. So the molarity of both hydroxyl ion and hydrogen ions will be same. Now you substitute this value in the previous formula we found, Kw. Kw is hydronium ion concentration multiplied by hydroxyl ion concentration, and as I have already told you, this is actually H plus ion concentration. When you substitute the values, you get 1 into 10 power minus 14 Kw value, and it will be obviously molarity square because molarity multiplied by molarity will be molarity square. You can write it m square or you can write mole per liter whole square, that is mole square liter inverse 2 also. The value of Kw is temperature dependent as it is an equilibrium constant. So equilibrium constant can change only with temperature, otherwise it cannot change for a particular reaction. So this value you will be using 10 to the power minus 14. We will be using this formula, right? Kw equals to S3 plus ion concentration, OH ion concentration, and it is equal to 10 to the power minus 14 if the temperature is not given, or if the temperature is given as 298 Kelvin. In that case, we will be using this formula directly. Okay, quite frequently. So just remember, we will be using it. The density of pure water is 1000 grams per liter and its molar mass is 18 grams per mole. We know that, okay? The density of water is 1 gram per ml, 1 gram per ml or 1000 grams per liter. And its molar mass is 18 grams. So from here, we can say the molarity of pure water. What is molarity? Number of moles divided by volume in liters. We can calculate from here. The concentration, that is molarity of water, will be number of moles, okay, in 1 liter. And remember, here we are talking about per liter. These 1000 grams are present in how much volume? 1 liter. So it means if I get from this 1000 gram, I can get how many moles are there, okay? So number of moles divided by volume, which is actually 1 liter, will give me molarity. So number of moles divided by volume, number of moles given mass divided by molar mass divided by volume 1. So it will give you 55.555, or you can say, if you round off, 55.56 also. Now, when you get the molarity, the ratio of dissociated water to that of undissociated water can be given as 10 to the power minus 7 divided by 55.55. Why? Because this is the molarity of water, 55.55 m, and if I go back and tell you, here it is 10 to the power minus 7 moles per liter. Means dissociated. Only this much got dissociated. Try to understand what I am saying here with the reaction. You have H2O, it gives you H plus and OH minus. Okay. Now here at equilibrium, the concentration of water is 55.55. This is 10 to the power minus 7. This is 10 to the power minus 7. Okay. Basically, initially it was 0. Try to understand. Initially it was 0 before equilibrium. Okay. So if you have just water, undissociated water, then it will be 55.55 moles per liter. Okay. So it is initially. Then at equilibrium, suppose first change. What change took place? You got 10 to the power minus 7 H plus ion, 10 to the power minus 7 OH minus ion. It means here 10 to the power minus 7 got dissociated because the ratio is 1:1:1. So if you get 1 mole here, it means 1 mole got dissociated. If you got 10 to the power minus 7 moles, 10 to the power minus 7 moles got dissociated. Now at equilibrium, it will be 55.55 minus 10 to the power minus 7. This will be 0 plus 10 to the power minus 7, 0 plus 10 to the power minus 7, that is 10 to the power minus 7. Now this is actually 55.55. If you subtract 10 to the power minus 7 from 55.55, it is not going to make any change. 55.55. Okay, so what is dissociated? Dissociated only this much. Only this much got dissociated. And undissociated 55.55. This is the ratio. It will give you 1.8 into 10 power minus 9. That is approximately, you can say, 2 into 10 power minus 9. So thus equilibrium lies mainly towards undissociated water. There is hardly any dissociation. Hardly any dissociation. So most of the water will be in the form of undissociated form. Hardly any H plus or OH ions will be there. There will be, but very, very few. We can distinguish acidic, neutral and basic aqueous solutions by relative values of hydronium ion and hydroxyl ion concentrations. Hydronium ion will represent acidic character, hydroxyl ion will represent basic character. Okay, because if H plus is released, it is acid. If OH minus, as per Arrhenius concept, it will be base. So that's why they will represent acids and bases, or acidic and basic character. So for acidic character, hydronium ion concentration will be greater than hydroxyl ion. So suppose you have 4000 hydronium ion and 3000 hydroxyl ion. Okay, so what will actually happen? 3000 hydrogen ion will combine with 3000 hydroxyl ion will give you 3000 water molecule, and this is neutral. Okay, here 1000 now H plus ions will be remaining and 0 hydroxyl ions. So 1000 hydronium ion or hydrogen ion will make the solution acidic. Simple concept. So that's why if you have hydroxyl ion greater than hydronium ion greater than hydroxyl ion, it will be acidic. If you have both equal, it is neutral. If you have hydronium ion less than hydroxyl ion, in that case, this will be in excess. The solution will be basic.